unmute themselves and ask questions or type them in the chat. Rahil, if you can.
Yeah, am I audible?
Yeah, you're audible.
Okay, and I'm sharing the screen. Can you see it?
Yes.
I can't see your screen. Yeah, now I can.
Yeah, okay. Hello, everyone. I'm myself, Rahil. And so our today's topic is lock and key with RSA. This is actually, I'll tell about actually RSA Cryptosystem. I'm sure everyone among you know what is a cyber security, right? Hello, guys, you know?
Yes.
Yeah, yeah. Okay. So the security system of our cyber world. So in the real world, whenever some kind of crime like robbery or murder or any kind of violence happens, then there are policemen, soldiers who fight and save us. So, but nowadays, many of our important information like emails, social media accounts, websites, any kind of internet banking or phone pay things, their passwords, everything related to them are in our cyber world. Uh, so as like the real world, the cyber world should also need a security system to protect our computers, electronic systems, server, mobile phones, network, and many other data from cyber attackers like hackers and cyber criminals. So, so now, are you familiar with the terms cryptography and cryptosystem? Can you explain anyone? Okay, so the word cryptography formed by the words cryptos, which means hidden or a vault, and graphene, which means writing. So the cryptography actually means something secret writing. Uh, so actually, this is a technique to protect our information and communications by using some kind of codes and algorithms. And what is cryptosystem? What is the difference between this cryptography and cryptosystem? Actually, cryptosystem contains those cryptographic algorithms so that only a single person or that person can read or access the secret information to whom those are written. So we can say it like cryptosystem is a key to access those secret information. And in nowadays, there is an ample of applications of cryptography. So the fundamental application is to construct a protocol that prevent a third party or a public from reading or accessing a private message. Like say we have this is a message and we have two persons, Alice and Bob. Okay, so this is a message, and Alice is want to send this message to Bob, and this is of course this is secret, and there is a third party called Tom. So so he can be a cyber attacker. He can be uh, uh, he can be CID or anyone like he may be a private investigator, and this is the thing which we want to Alice want to send to Bob such that Tom cannot access it. So he can produce an algorithm so that Tom cannot access it. So he just produce the algorithm and send it to Bob. So so even if Tom gets the algorithm, he cannot decode it. So that's why uh, cryptography prevents a third party or a public from reading or accessing some private message. But nowadays, the cryptography is used in various aspects of information security, like data confidentiality, data integrity, data authentication, also in electric commerce, chip-based payment cards like the Visa card, or I should say debit card or credit card. So and digital currencies, computer passwords, military communications, digital right management, and even copyright violation. So, uh, so this is very much useful and rich technique thing. So I'll tell you some terminologies. So let us go back to that Alice and Bob experiment or story. So Alice has the message, the secret message, and this secret message in its original form is known as uh, the plain text. Okay, and Alice is trying to send this plain text to Bob in such a way that uh, nobody other than Alice and Bob can access it. So he just make it an unintelligible form, and this is known as the ciphertext. And nobody cannot use it. Nobody can use it. So uh, this is known as ciphertext. Okay, and the process by which Alice is making the plain text into a ciphertext is known as the encryption. And when Bob gets that ciphertext, he need to get back the plain text from this ciphertext. So he just decode it and get that plain text back, and this process is known as decryption. Okay, so these are the 4 terminologies you should know to study the crypto system. Okay, so but when if we just process we just process with numbers, no, 1 2 3 and so on. But if we have some take message like I am coming tomorrow, like that, so we just need to produce this alphabets into some numbers. So we use this type of table. ASCII table is one of them. The full form is American Standard Code for Information Interchange. Anyway, and here the capital letters, small letters, and other signs are denoted as some by some alphabet, by some numbers. And we have another technique, that is we just put A is equal to 0, B 1 0 1, C 0 2, and so on, so that something we can make my name is say Rahil. Okay, so this can be written as R for 17, then A for 0 0, H for 0 7, 0 8, and 1 1. So my name is can be written in by using this number. Anyway, uh, let's see some historical stories, uh, and this history is really interesting. So in the ancient times, the kings used to rearrange the alphabets of a secret message while sending it. Like the hello word can be written as EHLOLOWRDL, something like that. Also, they uh, they used to replace some English alphabets with Latin or Greek alphabets. Like can be written as this is just an example. Can be written as maybe theta, alpha, eta. So this is it, theta, alpha, eta. So you'll see this is interesting. And another thing, that is Julius Caesar, the famous emperor, used to replace a letter with a shift of 3 of positions further down the alphabet to communicate with his general. Like math can be written as PDWK, just I'm showing M, and instead of M, they used yeah. Instead of M, they write MNOP. So instead of M, they write P. So instead of A, they write uh, D. Similarly, instead of T, they write W, and instead of H, they write K. Uh, so image can be written as PDWK. Also, in the David Kahn, in his book The Code Breakers, the story of secret writing, in 1967, he noted that modern cryptography was actually originated among the Arabs. Uh, and Al-Khalil wrote the Book of Cryptographic Messages, which contains the fast use of permutations and combinations to list all possible Arabic words with and without vowels. But the most interesting thing is that the earliest known use of cryptography is some carved ciphertext which found in some stones in Egypt. So pyramid is not only the mystery. Okay, so now I'll tell public key cryptosystem. Actually, this type of cryptosystem uses a pair of keys, a public key and a private key. The public key is not secret and this can be accessed by anyone. But the private key is actually the secret one and can only be accessed by that person to which the message is sent. Like we just go back to that Alice and Bob story. That is, if we have the public key, let us say that EU, the public key can be accessed by A, can be accessed by B, even can be accessed by Tom also. But the private key is the secret one. Okay, PR. So this secret one, this can be accessed only by A, that is Alice and Bob. But can but Tom cannot access that private key. But, because uh, from the public key, Tom cannot compute the private key. That is, Tom don't know how to compute the private key from the public key. Okay, so I should mention one thing. Using the public key, one can encrypt a plain text, and to make it a ciphertext, and to decrypt it, one has to use the private key. And an interesting thing is that the private key is generated from the public key by using some cryptographic algorithms based on mathematical problems. Okay, so I mentioned that Tom cannot access the private key actually because the cause of it is Tom don't know the cryptographic algorithms. I mean, which using which cryptographic algorithms they have to decrypt it. Tom don't know that, so Tom cannot access the uh, message as Tom don't have the private key. Okay, so now our today's topic is RSA cryptosystem. RSA was the first public key cryptosystem named after the inventor's uh, history man. So by the first letter of their name, we just write RSA. So the RSA. So the RSA. Uh, and the main thing behind this RSA is it is based on the difficulty of finding the prime factors of a composite number. That is a composite number. Actually, which is the product of two large primes. So, if we have a composite number n, which is the product of two large prime numbers, those three are not only prime numbers; they are large prime. And if you are given an integer which is a product of two large primes, it is really difficult to factor it into this two prime numbers. So on the basis of that difficulty, these three mathematicians uh, derived, invented that crypto system. So we'll discuss the method to generate public key to encrypt a message, as I said earlier, and to generate how to generate a private key from the public key, and how to decrypt the message using this RSA algorithm. I'll discuss all of them. So now the key generation, and before beginning, I would ask some questions to you. Okay, so do you know what is Euler's? What is this? Okay, I'm just telling the name.
Yes, sir.
Python.
Yeah.
Yes, sir.
Yeah. Tell me, anyone.
Sir, the number of
Five
the
function or
coprime
two
numbers
function.
which are before n, less than n.
So the number of numbers which are co-prime to n and less than n.
Yeah. Nice. Euler's phi function, and this is the number of integers. Actually, I should say number of positive integers, uh, which is less than or equal to n, and GCD of a and n is equal to 1. I mean, this is the I shouldn't write like that. Uh, this is the number of co-prime integers, which is less than or equal to n. Okay. We'll get back to this thing. So we have the number n, which is the product of two large prime numbers, p and q. Then okay, so one more thing. Can anyone tell me what is the value of phi of p?
So P minus 1.
Phi. Explain why.
So
Sir, because if p is a prime number, then before that, no other number has HCF more than 1, which are less than p with respect to p. So that's why there are p minus 1 numbers starting from 1 to p minus 1, which are co-prime with p.
Yeah, very good. So can everyone understood what he's saying?
yes, sir.
Yes, sir.
Yeah. So he's basically saying that 1, 2 till p minus 1. These numbers are less than p, and every number is strictly co-prime to p. So there are total p minus 1 numbers less than less than p, and which are co-prime to p. So this is equal to 1. And now, can anyone tell what is multiplicative function?
So those functions for which f of mn is equal to f of m into f of n for co-prime integers m and n.
What is co-prime? What co-prime integers come from? Hello, tell me.
So like for those that are true for all, they're known as completely multiplicative, but those that are only multiplicative, for those it is only true for co-prime integers m and n, I think.
No, actually, this is not a matter of co-prime integers. Okay. Can anyone else want to try?
So multiplicative functions are those functions, suppose if A into FB is equal to FAB, where the GCD of A and B is equal to 1.
Yeah, good, but
If of one is equal to 1, and f of a times b is equal to f of a into f of b, and where a b GCD is equal to 1.
yeah, but you don't need that GCD thing. Actually, if we talk over real numbers, then just this thing is only the definition of multiplicative function. Anyway, okay, so
But it is called completely multiplicative if it is generalized.
yeah, you can tell it. Okay, so do you know Euler's phi function is multiplicative function?
Yes.
Yes, sir.
Yes, sir.
Yeah. Okay, so what is the value of phi of n?
So P
Phi
minus
of
1
n
into
into phi
Q
of
minus 1.
Yeah, good. P minus 1 times, sorry, is equal to phi of p times
Okay.
phi of q, and this equal to p minus 1 times q minus 1. Okay, so we just choose some integer e which is less, which is strictly between these two things. And this e is and one more thing. And one more thing, we have to make sure that the GCD of E and P minus 1 times Q minus 1 should be equal to 1. So we have to choose such some E between 1 and phi of n, that is such that the GCD of E and phi of n is equal to actually 1. Okay, and this E is actually our encryption key. Encryption. Okay, now we'll find the decryption key. So we have the encryption
Sir,
key. Yeah.
sir, the encryption key is not unique. And
Yeah.
there can be many integers. Like there can be phi of n integers which are possible for E.
Yeah. Actually, E is given. I'll get. I'll explain this in a while. Okay. Of course, E is not unique.
If it's not unique, then how can
E is not unique. Of course, E is not unique.
we? Okay, that's what makes it tough to decrypt. Okay.
Yeah, yeah. And I'll show more things on just wait a while. Okay, so we have encryption key is E, and we have given n. So the public key and the n is called the RSA module. So the public key is the pair n and e, and this is given to us. I mean, when someone is trying to encrypt some message, then he just pick some e and just encrypt the message, and this is a public key, so everyone can access it. Okay, so
Is
using
n
this,
given?
yeah, n is given. Of course, n is given. N is given and e is also given.
Okay, some random is given.
Yeah, some random.
How is n determined? Like, there is a range for n.
No, n is the product of two large primes, and
Okay.
it will be better that if we choose some large, I mean very large prime. Some mathematicians use 10 to the power some large numbers, and such that p is larger than 10 to the power some large number. something like that. Anyway, so now we'll see the how to find the decryption key D. So the restriction for D is similar to that. And please mute your mic. Hello. Yeah, fine. Okay, so the restriction for D is also in between these two numbers, and we just have to find such D such that DE is congruent to 1 in mod I. Yeah. So do everyone is familiar with this notation?
Yes.
Tell
Sir,
me
you
what
are
is
talking about the congruency.
yeah. What does that mean?
So C divide.
They will
When
use the
A
C
is
reminder.
divided by C, the remainder is B.
Okay, so one more thing. Do you say? I mean, can anyone say that such a D exists or not?
Yes, sir.
It is a
Because
multiplicative inverse, right?
yes, sir. And E and phi of n are co-prime, so such a D will exist.
Yes.
No, you just cannot tell that multiplicative inverse or something like that. Do you know? Do you heard the thing called Bezout's lemma? Or Bezout's theorem?
Bezout.
Yeah,
Yes, yes, yes.
tell me. You are not clearly audible.
Sorry, it means modular inverse, not multiplicative.
Okay, but how can you assure that such some inverse exists or something like that?
Yeah. E and phi n are relatively co-prime, right? Relatively prime, right?
Yeah.
So that's there's a if and only if condition on the existence of multiplicative modular inverse for that. So this will exist in this case.
Yeah, but tell this something a bit mathematical.
Yes, so we can use Weber's theorem and say that since GCD of E and phi of n is 1, that means that there are integers x and y such that ax plus phi of n into y is equal to 1. And that means that there is an integer x such that ax is congruent to 1.
Yeah, very. Okay, so Bezout's lemma, according to Bezout's lemma, for some integer a and b, there exists some integer x and y such that ax plus by is equal to the GCD of a and b. So that is the Bezout's lemma. And here, here the two numbers are e and phi of n. Okay, the GCD of E and phi of n is equal to indeed 1. So which we have Ex plus phi of n, that is P minus 1 times Q minus 1 times Y, and this equal to 1. And if we take uh, the mod with respect to P minus 1 times Q minus 1, then we can get the relation like that. And this is actually this relation, and this x is equal to d when x is in that range, and if x is not in that range, then we just add or subtract some. We just add or subtract some multiple of p minus 1 times q minus 1 from x, so that we can find d, which of course lies between 1 and phi of n. Okay, anyone, someone is trying to say something.
So, sir, we have to take E such that it is always co-prime with phi of n.
We have to take some E, such E, yeah. The restriction on E is ER that.
Okay.
And the restriction over D is that and that. Okay, so we have the pair N and E is the public key, and using this N and E, we can find the integer D, which is a private. So let us do some math. Okay, so I am giving that N is equal to 1, 2, 4, 7, and uh, just tell me, can you factor it?
It is 29 times 43.
Yeah.
20, yes.
Okay, so what tell some possible value of E. Okay, so now this thing comes that E is not unique. E is not unique. So tell some possible values of E. E is strictly between 1 and 5 of n, that is 28 times 42.
Sir, then 5 will be one such case, I think.
Yeah.
So then it can be 11 also.
13
Yeah.
also.
Yeah. Then okay, I just help you some with some method. That is 28 is 4 times 7 and 42 is
6 times 7.
6 times 7. Okay, so this is actually 2 to the power 3 times 3 times 7 to the power. So everything other than the everything co-prime to this are some values of E. So 11, 13. It cannot be equal to 15. So it can be 17. Also some composite numbers like 55, 65, and so on, 85, anything. Okay, so let us take some public key. N is equal to 1, 2, 4, 7, and let us take E is equal to 5. Okay, so find D. Find D. Okay, so I just write the restrictions for D. It will help you.
Sir, 499.
499.
So I'm
Let
between
us
941.
4. Sorry,
941.
941. Okay, so let's check it. Just check it and tell me. I have to. No, I think.
Sir, I think 941 can be.
499 is not. Okay, so let me check. 5. Yeah, I think. Yeah. 941 can. Okay. Can you check it that just also we can see that if we try d is equal to 941, this works. Okay. So can you find another value of d?
So we can just add 1176 as multiples.
So, but we can't do that.
No,
Because it's
actually
less than
we cannot take we cannot multiply or add some multiple of 1176. Actually, then
Oh, yes, sir.
it
Yes.
will be out of that range.
Yes, sir.
Yes. So I think there will be only one such.
Do you really think so? I have another. Yeah, you are right. Yeah, I did a mistake in my rough work. Okay, sorry. For some E and N, for some N and E, the D is unique. Okay, but E is not unique.
So D is unique for one.
Yeah, D is unique for.
But D is unique for every.
I cannot hear you clearly. Hello.
Hello, sir.
Yeah, I cannot hear you clearly. Anyway, I'm continuing. For some given E and N, there exists only one such D in that range. Anyway, let's see the encryption process. Okay, maybe I am wrong. So you can check that uniqueness thing, after the talk or any other time. Okay.
So why
Sir,
did we
is the
exclude
unique or
499?
the unique modulo n? Sorry, modulo phi n.
Yeah.
Sir, is D unique or D unique modulo phi n?
D is indeed unique. Actually, D is in that range, and we were taking the modulo with respect to that, so D should be unique. Okay, I got the point. So we said that by Bezoar's lemma that X and Y are unique. Okay, so there are X and Y are unique if X and Y are in that range. How should I explain?
So why did we exclude 499?
Because just multiply by 5. Try to multiply uh, by 5. I mean, just check this.
So it is coming one mod 1247.
I think we have to take 1176 mod, not 1247. That means mod of phi n, not mod of n.
Yeah, one moment. One 176. No, if I think you have calculated some mistake. There is some. This is 1176 cannot divide this. You just check once again. At 1176 cannot divide that. Hello.
Yes, sir.
Yeah. So I think you have done some calculation mistake. You just check once again that 499 times 5 minus 1 is a multiple of 1176 or not. Because I have also checked, but it is not working. Okay. Anyway, I'm proceeding to the next step. That is how to encrypt some message. So let us take the message as m. M is an integer. If m is not an integer, then m can be expressed as an integer, as I said earlier. That I showed
Sir,
ASCII table. Yeah.
like can we encrypt names using this?
Yeah. I showed you. No. Uh,
Using ASCII we can, but using RSA?
one minute. I have shown you. No. Where is it? Yeah. This is it. So I've shown this. That a name can be written as a number, then we can use RSA algorithm on this number.
Okay, we will use RSA on this number. Okay.
Yeah. Okay. So if we have the plain text m, and we also have the public key n and e. So we just encrypt m as m. We raise m to the power e, and this is congruent to c in mod n. And we just have to calculate the remainder of m to the power e while divided by n, and this c is our cipher. That is the encrypted text and encrypted message or number, I should. And one more thing.
Can you please repeat how you got that number m? I think I missed.
Yeah. Actually, a number m is the plain text which is a message in its original form, and we have to choose such sum n, that is such sum p and q, such that n is strictly greater than n, and the GCD of m and n is equal to 1. So we have got we already have our plain text. Then we just have to find such n and e, so that we have the public key. Then we just have to take m to the power e and the remainder while dividing by n, and this c is the cipher text.
No, I understood what the plain text is. I want to know, I mean, how are you representing the plain text using that integer m? I mean, how are you encrypting it to find the number m? I can't understand that.
We don't encrypt it to find the number m. We just encrypt m to find some other number.
No, yeah, I meant that only. I mean, we have the plain text first, and
Yeah.
then it's written that we represent the plain text space by the integer m. So how
Yeah.
are we getting that integer m?
There are many processes, like one I showed that we can use ASCII table, or we can use this method, and there are other methods also.
Oh, I see. Thank you.
Yeah. Okay, so this way we can get our ciphertext, and this is the encryption process. And before going to the decryption process, let us do some math. Okay, so if m is equal to 15, and as our previous problem that n and e is a pair 1, 2, 4, 7, and 5. So tell me what is the value of c?
M is 15.
Yeah, m is 15, and n and e is a pair that. So basically we have to calculate 15 to the power 5 in mod 1, 2, 4,
Sir, it's
7.
1199.
Yeah, right. I'm not explaining how you have get it. Actually, this is an element. It is very simple.
I use
Now,
calculator.
great. Actually, I have.
Is there any mathematical method to do this?
Yeah. No. You just have to calculate 15 to the power 5. The value is something 75937. Yeah.
Sir, is the M given to me, or is it randomly selected?
What m? Yeah, m is the plain text. That is, Alice is trying to send her message m to Bob. So m is of course given. Okay.
So how do we get to know that M is co-prime to N?
We have to choose such some n. Of course, we have to choose such some p and q, then such so that n satisfies this thing. You get it?
Okay, sir. Thanks.
Yeah. Now the decryption process. Achha, before telling you the theorem, I would like to ask something, that is, do anyone know what is Euler's theorem?
So a to the power
Yes,
5
sir.
is congruent to 1 mod.
Tell one by one.
So e to the power 5n is congruent to 1 mod n.
So where N in a paper.
Is there any other condition?
Sir, one thing
A
n
and
must
A
be co-prime.
A must be
be
co-prime to
co-prime.
N.
Yeah, very good. Yeah, this is the Euler's theorem. So we will use Euler's theorem to prove this theorem. So the theorem says that let n and e be the public key and d is the corresponding private key. Then m to the power e to the power d is congruent to m in mod n. Did I show how to find the value b? Yeah. You know the value of d. Okay, so can anyone prove the theorem?
Yes, so yes.
Yes, sir. So we can write this will be equal to m raised to ed. So that ed can be written as phi of n into k plus 1. And using this theorem, we'll get that m raised to ed will be equal to congruent to m1.
Yeah, go on.
Yes, sir. So we can put that, substitute that, and we'll get m raised to e raised to d will be m raised to phi n.
Yeah, yeah, okay, very good. Yeah, I just explained this once again. That is, we had ed is equal to phi of k, phi of n times k plus 1 from this thing, from this thing, or uh, from the condition over d and e. So ed can be written as phi of n times k plus 1, and then m to the power e whole to the power d is actually equal to m to the power ed. Then we just replace ed by phi of n times k plus 1, and then write this in that form. Then m to the power k whole to the power phi of n, and this is congruent to actually 1 in mod n. Why? Since we have m and n are co-prime, and since m and n are co-prime, so m to the power k and m can also be co-prime. So m to the power k whole to the power phi of n is congruent to 1 in mod n, and there is another m, so the total thing is congruent to m in mod n. So we had the ciphertext C, right? So C is actually m to the power e uh, is congruent to C in mod n. So we had the C. So we just take this to the power the decryption key d. So this actually equal to C to the power d, and C to the power d is actually then becomes congruent to m in mod n according to our theorem. So this way we can decrypt uh, the ciphertext. Okay, so now now let us do some problem. So yeah, let us use that problem. We had n and e is equal to
So, so for decrypting, we'll just raise the ciphertext to the power of d, and then we'll find that modulo.
your audio is not clear.
So for decryption, we will raise c to the power of d and then find modulo.
No, I cannot understand what you are saying. Like it is your audio is breaking.
Hello, sir. Can you hear?
You can write this in the chat. And tell me after writing, and I am proceeding right now. So the pair is 1 2 4 7 and 5, and the e is equal to 5. Then we have calculated that d is equal to 941. Can you remember from here 941? Okay. And we had m is equal to 15. uh, then what was the value of c to calculate it? C is
1199.
1199. Yeah, we had c is equal to 1199. So tell me, just I'll show that c to the power d, that is 1199 to the power 941. This is actually equal to 15 in mod 1247. Uh, I am showing this. Okay, I just uh, show you. Uh, I have I just write it once again. 1199. So we have 1199 to the power. What was this? It's 941, and I just take the mod over 1247. This is actually 15. So this is Python anyway. So we have shown that. Okay. So what next? So RSA is a public key crypto system. But if you want to encrypt some secret message using RSA algorithm, how can you be so sure that your message will remain secret? I mean, is RSA secured? So, like maybe a cyber attacker can also compute the private key D, right? From the using the public key N and E. So how can we be so sure that using RSA we can completely secure our information? So now I'll tell that. So it can be shown that computing D from a pair N and E is as difficult as finding the prime factors P and Q of N. So through this doesn't prove that the difficulty of computing the secret key is difficult, but it can reduce the problem to that of a famous problem, the factoring problem of integer. Like if I give some number n to be n is very big number, like it can be greater than 10 to the power say 100. So or more big number. So it is really difficult to compute the prime factors p and q. So this says that our problem can be reduced to that problem of finding the factors of and we don't know how to factor a sufficiently large integer in, as we cannot proceed by trial and error. No, so we just have to choose such some appropriate p and q and such some n, so that finding p and q from n is really difficult. And there are some things related to the choice of p and q. To make the factorization of RSA module n infeasible, we have to choose p and q appropriately, that I have said earlier. So one thing about p and q is we have to pick them so large. And one more thing, do you know Fermat primes?
Yeah.
So primes of the form 2 to the power 2 to the power n plus 1.
Yes.
Yeah, good. And Mersenne prime?
So 2 to the power n minus 1.
Okay. So if p or q are in those special forms, then it will be easier to find to factor in, as there are many theorems related to the multiplication or factors of those special form special prime numbers. So we have to avoid this type of primes while choosing p and q. And also we have to keep in mind that there are other factoring algorithms, like there are AKS primality test and other stuff. So we have to keep in mind those factoring algorithms and avoid choosing such some P and Q, so that we can one can easily factor it.
Sir, how can we make sure that n can be factored in exactly to P and Q where P and Q is prime?
Actually, we just calculate the n and give to while I mean before using this n as a RSA
Say,
module.
for example, I have encrypted my name in that form using that ASCII code. Then first I need to check that n can be factored in exactly to such P and Q, not many more. So how can we guarantee that?
Yeah, this say this is your name, and this is actually equal to n, and we have to choose some P and Q such that the product of PQ is equal to n, and which is strictly greater than n. So we can always find such some n, right?
Yes, sir. Yes, sir.
Okay. So there are some restrictions over E also. So can you tell me, can E be equal to 2 or not?
No, so I don't think E can be equal to 2 because one of the primes will be odd. So P minus 1 into Q minus 1 will be even.
Yes.
So E and E is co-prime to it, so E cannot be 2.
Yes, very good. So we have E and phi of n. This is co-prime, and phi of n is equal to P minus 1 times Q minus 1, and these two things are indeed even. So E cannot be equal to 2. But what will happen if we choose some smaller E, like if we choose E is equal to 3? Can anyone answer this? What will happen if we choose E is equal to 3?
So then the value of m will be larger.
The value of?
So value of m such means the C which will do that one will be larger.
Why? Explain this. M to the power 3. Then what is the guarantee that this is the remainder is larger? Tell me.
No, sir. I don't think we can tell like that.
Yeah. Okay.
I see one problem with a small for E.
Tell me.
The smaller E we have, the more forms of primes we can exclude. So if E is 3, then P and Q cannot be of the form 3k plus 1. And if E is 5, then it cannot be of the form 5k plus 1. So like as we increase the value of E, we can like reduce the number of the fraction of numbers that we are excluding.
Yeah, this is a point. And one more point. So anyone want to add? Okay. I just say we had ED is congruent to 1 in mod phi of n, right?
Yeah.
So if E is small, say E is equal to 3, then it is difficult to, it is very easy to find find the value of D, right?
If we use small e, then we can find out m easily.
M, why you are trying to find M? M is given. M is the message. You have M. You don't need to find such M. We have M. Okay.
Yeah.
Yeah. So it is when E is small, then it is easy to find the value of D. So the D is the private key, no?
Yes.
So if the finding the private key is easy, then the breaking RSA is easy. So that's why we cannot choose some smaller. And for just your knowledge, a popular choice for larger encryption exponent is is equal to 2 to the power 16 plus 1. So can anyone tell what is actually 2 to the power 61? 2 to the power 16 plus 1. Can you recognize the number?
So this is a Fermat prime, right?
Fermat prime.
Yes. This
Oh,
is
it's Fermat prime.
F1. 2 to the power 4 plus 1. Yeah, that's it. You can use. I have used these three things as the references, and Wikipedia is a common reference for us. And you can note down the book name, this book name, and this is interesting book. Anyway, so that's all. Thank you.
Thank you, Rahil. That was a wonderful talk. Are there any questions? Participants can unmute and ask.
Sir, so when Alice will be sending the message to Bob, then what exactly will he send? He will first send N, and then what else?
Okay, so Alice want to send the message M to Bob. So she just have to send. She have to find the value N, then have to find the value E, and encrypt M as this, and she will just send these three things. So C and the pair in. Alice will send this to Bob. Okay.
Okay, so from there, B can back calculate the value of M, and
Yes.
from there, it will get the value.
Yeah. So B have to calculate.
Can there be other values of M?
Yeah, all can. A can Alice can.
Satisfying this.
No, C is a remainder. So C is in that range.
Yes,
So,
but there can be other M's such that M power E leaves the same remainder divided by N. Right.
M power E leaves the same remainder.
Like there was a constraint now that M less than N. So yeah, sorry, it's unique.
Yeah. And when Bob gets this thing, I mean these three things, then he just have to calculate D from this pair, and then he have to calculate this thing, and he can get the M back.
So
what is D? Can you please repeat D? What is the thing about D?
D is the decryption key. Okay.
Is the decryption that part?
Okay, I'm just showing. Yeah, this is D. D is the decryption key, and D is in between 1 and P minus 1 times Q minus 1, and DE is congruent to 1 in mod this.
Hello, sir. Can you hear me?
Yeah.
So I have a doubt. So to decrypt the message, so if there's a hacker and he has the value of D, then it will be very easy to decrypt the message.
Yeah.
So then, so we have to ensure that D, we have to ensure that the Bob knows D without the hacker knowing D. So how do we ensure that?
Bob have to ensure what?
So we have to ensure that Bob knows D, but the hacker or any criminal doesn't know the value of D. So how can we safely send the value of D to Bob?
Actually, anyone Alice don't sending D to Bob. Bob has to calculate D by using this algorithm, and uh, as this is the fast public key crypto system, this is the we don't always use this technique, but this is one of the method to do this.
So if Bob can calculate the value of D, then the cyber criminal can also calculate. Because then they are public.
Yeah, that's a good question. I mentioned this here, I think. Breaking RSA. Yeah, I mentioned that a cyber attacker can also compute the private key D using the public key. Yes, he can find it, but but it also evident that he can I have mentioned the difficulty of finding the value of D.
Yes,
So
but then it will be equally difficult for the Bob to calculate.
so I don't know this thing. This is a good
So,
question.
what kind of things go to Bob? Like N, E, and D. N, E, and what? N, E, and C. Yeah.
Yeah,
And from that he calculates D.
yeah.
So can you say what Bob does after that, after calculating D? That's the thing. I mean, I want to know the use of D once.
After calculating D, the Bob have to
You will use the theorem.
yeah. So actually, m to the power e is equal to c. Is congruent to c in mod n. So he just have to rise to the c to the power d and in mod n. So then he can get m.
C power D will just calculate. Yeah.
Yeah, yeah.
Is this used nowadays? Is this system used nowadays?
Actually, this is the first step of the things we are using now. So yes, you can say that we don't use directly this, but we use a modified form of this. Actually, the next step of RSA is the Rabin crypto system. So
Can you repeat?
you can start your the next step of RSA is the Rabin crypto system. So after RSA, there are many kind of crypto systems have invented, and RSA is the first step. So this we have interest in that. So the things we are using now is actually I mean comes from RSA. You can say comes from the concept of RSA.
So as
Oh,
the
the
scientists have
principles are the
modified
same.
the RSA system, so that means that there is something defect in the RSA system. So what is the defect?
Yeah, the breaking of RSA I have just explained. But actually, the breaking of D is as difficult as finding the prime factors of P and Q, but it haven't yet proved that we cannot factor some n or not. So breaking RSA is difficult, but not impossible. So that's it.
Okay, got it.
Anyone else?
The systems that we use today, do they follow the same principles as RSA?
That thing I don't know actually. You need to ask some engineers or someone who are doing research over this.
Okay, okay.
Sir, are the encryption systems exposed publicly?
Actually, this is irrelevant of mathematics thing, and I don't know. I have just explained the mathematics behind RSA and the modern crypto system, and how the investigators or the government or anyone else use it. I don't know actually.
Are there any other questions? If not, we can end the meeting here, Rahil.
Yeah.
Okay. Thank you, Rahil. Thank you, everyone, for joining us.